Picture a farmer in 1930s Iowa. He's pulling out of a freshly plowed field onto brand new asphalt in a massive tractor riding on steel lug wheels, spiked like an iron porcupine. Every rotation of those wheels tears chunks out of the new road surface, leaving a trail that looks like a dinosaur walked through. A couple of days later, the county sheriff shows up with a citation. A couple of months after that, the state issues a ruling. Vehicles with steel lugs off public roads, period. That's how the long history of bans in tractor engineering began. Many of these technologies were brilliant by design. They delivered fantastic traction, exceptional reliability, or a free boost in power, but precisely because tractors moved beyond the field, onto roads, into towns, into the reach of environmental and labor regulations, some of these solutions ended up under full or partial prohibition. Today we're going through 10 of them. For each one, I'll cover what made it ingenious, why the law ultimately shut it down, and what that cost the farmer. Stay to the end, because the final one is the most interesting. And if you find this useful, please subscribe. I'd really appreciate your support. Let's go. Before pneumatic rubber tires, virtually every tractor ran on steel wheels with welded or bolted steel lugs. Those lugs bit into the earth up to 4 or 5 inches deep, delivering near-perfect torque transfer. Steel didn't compress, didn't spin, and didn't eat power through deformation the way rubber does. Manufacturers like Ronaldson Tippett in Australia offered up to 10 lug designs for different soil types: dry prairie, sticky clay, wet meadow. In the field, these wheels were close to flawless. But the moment tractors started moving on public roads more regularly, it became clear that the tool perfect for soil was a weapon against infrastructure. Steel lugs destroyed gravel beds and the first asphalt surfaces, shattered wooden bridge decks and railroad crossing planks. Road departments and contractors quickly figured out who was responsible for destroying freshly laid roads and started lobbying for bans on lugged vehicles. By the 1920s and 30s, a number of U.S. states had passed outright bans on vehicles with steel lugs on public roads. Shoulders were sometimes tolerated, but getting onto the travel lane meant a fine. Familiar signs began appearing. Vehicles with lugs prohibited at town entrances and bridge approaches. Meanwhile, another technological revolution was underway. Firestone and other manufacturers were aggressively marketing pneumatic rubber tires for tractors. By 1930, nearly all new tractors still shipped on steel. By 1940, most serious farm machines came with rubber. The transition happened in less than a decade. Studies from the 1930s showed that on roads, rubber tires saved up to a third of fuel and allowed operators to get up to a quarter more work done per shift, thanks to higher road speeds and less vibration loss. But in heavy mud and unbroken ground, steel lugs remained the gold standard for grip for years afterward. Many farmers switching to rubber held onto their steel wheels just in case, pulling them out for the deepest tillage work. What's interesting is that the steel wheel debate didn't end in the 1930s. In Iowa, in the 2010s, Mitchell County officials tried to ban steel-wheeled tractors from roads after a Mennonite religious community continued driving spiked tractors on county roads, damaging recently resurfaced pavement. The Mennonites, for whom the use of steel wheels is tied to religious conviction, challenged the ban in court, and the Iowa Supreme Court ruled that such a prohibition violated First Amendment religious freedom protections. As a result, road crews are forced to absorb the additional repair costs, while religious farmers continue using a prohibited technology that's nearly a century old. Steel lug wheels remain a brilliant solution for soil traction, one that lost not to superior engineering, but to politics and the growth of the road network. In the modern world, their niche has shrunk to small communities and museums, but the core idea, rigid traction transfer through ground-engaging cleats, lives on in modern steel tracks and aggressive lug tread tires. Starting a tractor today means turning a key or pressing a button. In the middle of the 20th century, it was closer to a duel between a man and an engine. The hand crank was the standard way to start tractors and automobiles from the beginning of mass motorization until the electric starter became widespread. The concept is simple. A square or splined socket on the end of the crankshaft accepted a removable handle. The operator turned it with real muscle, spinning the engine until it caught and ran on its own. On tractors with big, slow-turning cylinders, this required considerable physical force, especially in cold weather. Thick oil, high compression resistance, and stiff mechanics combined to make it a serious workout. The danger was something called kickback. If the ignition timing was set too far advanced, or the mixture fired before the piston reached top dead center, the engine tried to spin backward, violently throwing the crank handle in the opposite direction. Medical journals in the early 20th century even coined the term chauffeur's fracture, a characteristic break of the radius bone caused by the crank handle hitting the wrist or forearm. The most famous victim of such a blow was Byron Carter. In 1908, he stopped to help a woman whose Cadillac had stalled. He leaned over the crank, gave it a pull, and took a full-force blow to the face when the handle kicked back. A broken jaw led to infection and pneumonia, and Carter died. Cadillac's president, Henry Leland, shaken by the death, tasked engineer Charles Kettering with developing a safe way to start an engine. The result was the first production electric starter, the Delco unit, which Cadillac introduced in 1912 and which effectively ended the hand crank era in automobiles. In agriculture, hand starting held on longer. Many tractors of the 1930s and 40s, including popular models from Fordson, International Harvester, and early Massey Harris, continued using the hand crank as either the primary or backup starting method. Farmers valued it for a straightforward reason. An electric starter depended on a battery and wiring, while a hand crank worked no matter what. Dead battery, broken wire, hard freeze. Over time, manufacturers and regulators moved decisively away from hand starting. Electric starters got cheaper and more reliable, and the injury toll from kickback and improper crank technique remained high. Safety instructions specified keeping the thumb on the same side as the fingers and pulling the crank only upward so a kickback would knock the handle free rather than trap the hand. But rushed or inexperienced operators regularly ignored this. There was no single global ban on the hand crank, but the electric starter became a required design element for machines falling under modern safety and ergonomic standards. The result? Hand starting vanished from new tractors and survived only in the world of vintage equipment. The genius of the hand crank was absolute independence from any power source, but the combination of physical demand and injury risk made it unacceptable in an era when the value placed on human health had fundamentally changed. The power takeoff shaft is one of the key tractor innovations of the 20th century. It allowed the engine's power to be transferred to mounted and trailed implements, mowers, balers, choppers, grain unloaders. But for decades, that power was delivered raw. The spinning shaft sat in the open with no guards or shields. Standard PTO speeds are 540 or 1000 RPM. At 540 RPM, the shaft makes 9 complete revolutions per second. If a sleeve, a shoelace, a piece of fabric, or someone's hair catches on a spinning shaft, the human body can wrap around it several times before the brain registers what's happening. Farm accident records and NIOSH incident reports show that such events almost always result in catastrophic injuries or death, amputations, multiple fractures, spinal cord tearing. Agricultural safety reports include real cases. A NIOSH FACE program report describes a 13-year-old helping his family on the farm. His clothing caught on an unguarded PTO shaft, and he died from multiple trauma before the ambulance arrived. In another case, an adult dairy farm worker caught on a partially shielded driveline. The guard had been removed or damaged and was also killed, wrapped around the shaft, in seconds. Accident analysis by occupational safety agencies showed that in the overwhelming majority of incidents, up to 70%, the PTO shield was absent, had been removed by the operator, or was damaged. The reasons are understandable. The guard blocked access for greasing the driveline, collected straw and dirt, and got in the way during servicing. Farmers took it off for a couple of minutes to make the job easier and often left it off for good. The regulatory response was firm. OSHA and state labor departments introduced requirements for mandatory functional PTO guards on tractors operated by hired workers. Manufacturers began shipping new machines with a master shield, a fixed cover over the tractor's output stub, and rotating shields on implement drive shafts as standard equipment. The open drive shaft as an engineering concept was brilliant in its simplicity and efficiency of power transfer, but in its bare form it was simply too dangerous. It was never literally banned. What was banned was operating one without protection anywhere human beings were at risk. Farmers still occasionally remove shields for convenience and continue paying for it with their lives and limbs, which shows how thin the line is between technical perfection and human nature. Look at American tractors from the 1940s through the 1960s, and you'll notice a strange configuration. Two big rear wheels and one narrow dual front axle pinched almost to a single point. These were called tricycle or bicycle front-end tractors, and they dominated row crop farming in the Corn Belt for several decades. The engineering logic was sound. A narrow front axle allowed the tractor to travel between rows of corn or soybeans without breaking plants or clipping them with the front wheels. Farmall and other manufacturers built machines that could turn nearly in place with remarkable maneuverability in tight headlands. For mechanical cultivation, hilling, and row crop work between the plants, this configuration was as close to ideal as it got. But the design had a dark side: stability. A narrow front track and a relatively high center of gravity made tricycle front tractors significantly more prone to sideways rollovers when working on slopes, dropping a wheel into a ditch, or catching the front axle on an obstacle. Stability research conducted by universities and safety agencies showed these machines had substantially lower rollover resistance compared to wide front axle tractors. The situation was made worse by shifting farming practices. With the arrival of affordable, effective herbicides, the need for repeated mechanical between-row cultivation dropped sharply. Farmers ran their tractors less often through narrow row middles and more often on general-purpose tasks: hauling, pulling heavy wagons, working rough ground. In those conditions, the advantages of the tricycle front end stopped outweighing its liabilities. No formal global ban on narrow front axles ever happened, but insurance companies and regulators began clearly favoring wide front machines. Many operations refused to buy tricycle tractors outright, and manufacturers gradually removed them from their lineups. A configuration once considered the pinnacle of row crop maneuverability came to be seen as an anachronism and a liability. From an engineering standpoint, the tricycle front end was a brilliant answer to a specific problem: working row crops with maximum precision. But once the farming practice changed, herbicides, wider equipment, different planting patterns, the problem itself disappeared, and the solution went with it: declared too dangerous for more general use. Historically, many tractors were capable of road speeds that sound absurd today. The Minneapolis Moline GTB, fitted with a highway gear ratio, could hit roughly 40 miles per hour on pavement, comparable to a truck. For a farmer with fields spread across a large area, that meant real savings in time getting from one place to another. The classic mechanical governor on diesel and gas engines limited RPM to protect the engine from self-destruction, not to comply with road regulations. Adjust it slightly or partially disable it, and the top speed ceiling disappeared. Farm folklore included entire oral traditions and written workarounds for unleashing a tractor for faster road travel. The modern legal environment works differently. In the European Union, for example, mandatory speed limiters are required on heavy trucks at 56 miles per hour. Tampering with a speed limiter carries serious legal consequences. In the United States, removing or modifying engine control systems, including speed limiters, in a way that affects emissions or on-road behavior, falls under the Clean Air Act and is treated as illegal tampering. In practical terms, this means today's tractor manufacturers hard limit maximum speed through software and protect those settings from user modification. Any attempt to flash or bypass the limiter voids the warranty and in the event of an accident or roadside inspection can trigger serious legal liability. From the farmer's perspective, an unrestricted governor and a fast road gear were a brilliant way to save hours on transit. From the standpoint of road safety and manufacturer liability in an era of dense mixed traffic, it turned out to be an unacceptable risk. Regulators essentially banned speed, leaving tractors to be slow road users and farmers to spend more time getting where they're going. For a long time, the tractor looked like what it literally was: a seat bolted to a frame between two rear wheels and an engine hood. No cab, no rollover protection, just open air and 360-degree visibility. Operators loved it. Easy to mount and dismount, nothing blocking the view, comfortable in summer heat. The problem showed up in the numbers. Tractor rollovers have been the leading cause of farm equipment fatalities for decades. NIOSH estimates indicate that roughly half of all fatal tractor incidents involve overturning, most commonly backward tip over while pulling, or sideways rollover on slopes. In Sweden in the 1950s, engineers developed and tested the first ROPS, rollover protective structure, a rigid frame or cage that creates a survival zone around the operator when the machine rolls. By the 1970s, ROPS requirements were spreading worldwide. Australia made them mandatory on new tractors in the early 1980s. In the US, major manufacturers voluntarily adopted ROPS standards for new machines after the mid-1980s. OSHA required ROPS on tractors operated by hired workers, but did not extend the requirement to self-employed farmers and their family members. Mortality analysis showed that voluntary standards weren't working. A Wisconsin study found that tractor-related fatality rates among male farmers actually increased from 10.9 to 13.6 per 100,000 between the early 1960s and mid-1970s, despite growing awareness of safer design. NIOSH estimated that if 100% of the tractor fleet were equipped with ROPS, rollover fatalities could be reduced by at least 70%. Formerly, no one banned the open platform outright. Old tractors still run without ROPS, and some farmers still remove installed roll bars to clear low-hanging branches or fit through old barn doorways. But in engineering standards and regulatory requirements, an open platform tractor as a new machine has effectively disappeared. Building and selling them that way for developed country markets is no longer possible, except for very small equipment in specific categories. The genius of the open platform was its simplicity, visibility, and ease of use. Its end came not from an engineering defeat, but from accumulated fatality statistics that made the absence of ROPS ethically and legally untenable. The classic diesel tractor engines of the mid-20th century ran fully mechanical fuel systems, inline or distributor-type high-pressure injection pumps, plungers, mechanical governors. These systems could run for decades with minimal service, tolerated variations in fuel quality, and had zero dependence on electronics. Farmers and mechanics loved them for their predictability. If an engine started smoking or lost power, you adjusted the fuel delivery, replaced injectors, or rebuilt the injection pump. All of it doable in the field with hand tools. No laptop required, no diagnostic equipment. Engines like the legendary International DT466 could rack up tens of thousands of hours before needing a rebuild. Then emissions regulations arrived and changed everything. European Stage 3A, 3B, 4, and then Stage 5 standards, alongside US. Tier 3 through Tier 4 final rules drastically tightened allowable levels of nitrogen oxides and particulate matter for off-road equipment, including tractors. NOx limits for heavy off-road engines dropped from around 9.2 grams per kilowatt hour in the late 1990s to approximately 0.4 grams per kilowatt hour under Stage 5, and particulate limits fell from 0.54 to roughly 0.015 grams per kilowatt hour. Achieving those numbers with a purely mechanical injection system is essentially impossible. What was needed was precise electronic control of injection, timing and volume, EGR management coordination with turbocharging and after-treatment systems. That meant common rail systems with electronic injectors, sophisticated ECUs, and entire chains of sensors. Mechanically, the old injection systems were engineering genius, simple and durable. They weren't banned head-on, they were regulated out of existence through emissions standards tight enough to force the entire industry onto electronics. The result, cleaner air, less NOx and soot, but far greater dependence on complex electronics sensitive to moisture, dust, and power quality. Asbestos is a mineral with remarkable properties. Heat-resistant, wear-resistant, with excellent friction characteristics. No surprise that from the mid-20th century it was widely used in brake pads and clutch facings, including those on tractors and other heavy equipment. A typical brake lining of that era might contain 35 to 65% chrysotile asbestos, combined with various binders and fillers. This delivered consistent friction coefficients under high heat, low wear, and long service life. Exactly what you want in a braking system on heavy agricultural equipment operating in harsh conditions. Over time, it became clear that microscopic asbestos fibers, when inhaled, accumulate in the lungs and lead to fibrosis, lung cancer, and mesothelioma, an aggressive form of pleural cancer. Research from the 1970s showed elevated mesothelioma rates among auto mechanics who regularly serviced brakes and clutches. They were inhaling dust while blowing out brake assemblies with compressed air, grinding linings, and disassembling components. Regulators moved to restrict asbestos use progressively. The EPA attempted a broad U.S. asbestos ban in 1989, including brake materials, but a federal appeals court overturned most of those rules in 1991, leaving restrictions in place only for specific product categories. In Europe and the UK, the ban was carried through completely. The UK prohibited asbestos in vehicles in 1999, the EU by 2005. Paradoxically, in the United States, asbestos technically remains legal in certain automotive and tractor brake and clutch products to this day, though usage has dropped dramatically and manufacturers have largely shifted to ceramic, organic, and other asbestos-free friction materials. In engineering terms, asbestos linings were close to the ideal solution for heavy-duty braking systems, but the long-term health toll on mechanics and operators made them unacceptable. The ban and the industry's departure from asbestos are a textbook example of a materially brilliant technology losing to medicine and epidemiology. Modern tractors meeting Tier 4 final and Stage 5 emission standards carry an entire after-treatment complex, a diesel particulate filter, catalytic converters, and a diesel exhaust fluid DEF/AdBlue injection system. These systems add substantial complexity, demand quality fuel and reagents, and can shut a machine down entirely when something fails. The response from a portion of farmers and mechanics has been DPF delete and DEF delete, physically removing the filter and disabling related systems through ECU reflashing. After such modification, the tractor stops regenerating the filter, often gains a bump in power and torque by removing system-imposed limits, and the risk of getting stuck in protection mode in the middle of a field drops. From a legal standpoint in the United States and most other countries, these modifications are prohibited defeat devices, hardware or software changes that circumvent emissions systems. The EPA treats any intervention that raises emissions above the certified configuration as a violation of the Clean Air Act. The legal consequences are serious. Penalties can reach tens of thousands of dollars per vehicle. One U.S. seller of delete kits was fined approximately $3.1 million for selling and installing DPF/EGR removal packages. EPA analysis found that defeat devices installed on diesel trucks and off-road equipment between 2009 and 2020, known to the agency, generated approximately 570,000 additional tons of nitrogen oxides and 5,000 additional tons of particulate matter. That said, regulators have acknowledged the legitimate needs of farmers operating in the field. In February 2026, the EPA issued a clarification emphasizing that farmers have the right to repair and maintain their own DEF and DPF systems including replacing components with equivalent parts that don't violate certified emission levels. But they do not have the right to physically remove those systems or reflash the ECU to disable them. From an engineering perspective, delete modifications are a brilliantly simple solution to a real reliability problem. Fewer complex components means fewer failures, but the environmental cost in increased NOx and soot emissions and the legal exposure have pushed this practice into the zone of outright prohibition. If mechanical injection allowed power gains through hands-on injection, pump adjustment, the electronic control unit era has its equivalent: remapping, reprogramming the injection maps, boost targets, and limiters. A modern tractor engine is often sold in multiple power configurations that differ only in the software. For example, a platform producing 150, 170, and 190 horsepower might be physically identical hardware, electronically throttled or opened depending on the spec ordered. That creates obvious temptation. Unlock the lower spec model to perform like the top of line without swapping a single mechanical part. Chip tuning companies offer two main approaches. The first is a full ECU reflash, rewriting the fuel maps, boost pressure targets, and smoke and temperature limits. The second is installing an external tuning box that intercepts sensor signals and fools the ECU into injecting more fuel or raising turbo pressure. From the farmer's perspective, remapping is free power, 20 to 40% more output from the same machine. From a legal standpoint, it's a potential Clean Air Act violation if the software change raises emissions or disables emissions control systems like EGR, DPF, or SCR. Industry resources like illegaltampering.org, supported by trade associations and regulators, explicitly advise farmers that such modifications are illegal and carry the risk of major fines and warranty voidance. Tractor manufacturers and dealers take a firm line. Farm Equipment Magazine and other trade publications note that dealers refuse to service machines with obvious signs of remapping until the factory calibration is restored, and warn that any ECU intervention voids warranty coverage. Research shows that pushing power beyond torque and thermal limits without accounting for those constraints can cause premature engine and drivetrain wear. Remapping has landed at the center of the wider right to repair debate. On one side, farmers argue that having purchased a tractor, they should be able to configure it for their needs and repair it without mandatory dealer involvement. On the other, manufacturers and regulators point out that altering the software takes the machine outside its certified emissions and safety parameters. Engineered well, remapping is a brilliant use of the design's built-in headroom, the ability to extract more from the same hardware and tailor the engine to specific tasks. But in the legal framework, it is increasingly treated as illegal tampering, particularly wherever it touches emissions systems. Every technology described here was born from a very specific, real problem. Steel lugs gave traction that rubber still struggles to match. The hand crank let you start an engine in any weather with no battery. The open PTO shaft and tricycle axle made tractors simple and effective tools. Mechanical injection, asbestos linings, and chip tuning promised more power, fewer breakdowns, or perfect friction. But the moment the tractor stopped being just a field machine and became part of a larger system, road infrastructure, environmental policy, labor law, the brilliance of these solutions ran into a different reality. Terrain, roads, the health of mechanics, the economics of insurance and legal liability started writing their own rules. Some technologies disappeared entirely, some survived in niches, and some came back in new forms. The Ferguson principles, for example, living on in simple tractors for the developing world. The history of banned tractor technologies shows that in engineering, it's not enough to be the best solution within the four walls of a shop or the boundaries of a field. You have to pass the test of society, law, and time. And it's on that test that engineers have to find the balance between brilliance, safety, and responsibility. Again and again.